All right, so what we are going to do next is, once again, look at some examples and apply Snell's law, okay? And just to remind you what is that, is just, okay, let me write it on upper corner over here. Is N1 sine theta 1 equal to N2 sine theta 2, cool? That's easy as that. And just to remind you what the N is the index of refraction. So it's by definition, so N is just the speed of light in the vacuum, the highest speed possible in our universe, divided by the speed of light in that medium. So in general, it will be larger than 1, and it's going to be exactly equal to 1 when you are looking at the vacuum. All right, guys, let's take a look at this one. So in the figure, a ray of light is perpendicular to the face AB. So that's on that vertical surface over there. It's a glass prism with the N given to be 1.5. Find the largest value of the angle phi, which is the apex of this prism over here, so that the ray is totally reflected at face AC, the diagonal one there. If the prism is immersed in air, let's try that one. All right, you guys want to give it a shot? Okay, I don't have that sound effect today. All right. Okay, cool. All right, guys. So first things first. So first thing first, it hits the AB surface perpendicularly. So you have to make sure that you keep in mind, every time that we do this, we use the normal line to be your reference all the time, right? So we have that. So when you have a ray of light hitting a surface in a perpendicular fashion like this, it means the incidence angle is 0. So when things go in 0, I mean, it's going to go out 0 because from Snell's law, it's going to be 0 equal to 0. So that means the light is going to just penetrate straight in. You guys with me? Cool. So the first interface is done. All right. So you don't have any refraction or anything, it's straight through. Now, once it hits that diagonal interface over there, now you have to draw the normal line all the time. There you go. That's your normal line. And that means the incident angle at this spot. So don't forget, I just want to remind you that every time we want to apply Snell's law, I think the easiest to look at this one is just the Snell's law at a point. Okay, we're just going to apply at that point. So what we have over here is incident angle is going to be this dude over here. Don't forget, we make a measurement of the angle with respect to the normal lines. Cool. All right, keep going. And the outgoing ray, all right, so I think you can guess in your head because you are coming from the glass out into the air. All right, so the glass having the end of what? Okay, let me put like N glass. That N glass is 1.5. Coming out into the air is 1. We approximate it to be 1. So you're going from large N to a smaller N. So it means you're going to go from a small angle to a larger angle. Does that make sense? So that means you can expect that, okay, if this is the incident direction, it's supposed to bend away from the normal. So I expect it's going to go something like this. So that means the refracted ray is supposed to make a larger angle than the theta. Bam. Cool. All right, so I hope this reveal how to pretty much look at this type of problems about the refraction, and you have sort of like the Snell's law relationship in your head. Cool. All right, but anyway, applying the Snell's law is not bad at all. So, okay, let me call this point like point P. Okay, so you say at P, okay, this is part A. At P, you say N glass sine theta, that's the glass side of the whole thing, equal to N air, and then you can call this, let me call this the alpha, shall we? That's the refracted beam going out. So it's going to be sine alpha. Cool. Almost done. Now, the theta is unknown, but that's easily done. I mean, you can calculate that easily because you look at this one, the apex angle is phi. So that's mean this one is going to be phi as well. Okay, it's just, you can look at it like it's like a similar triangles, or it's just like two parallel ray, and then you have the similar angle between those two corner over there. So that means your theta over here with the phi add up to 90 degrees. right? Make sense? These are 90 degrees. Cool. So that means you can write theta as a 90 minus phi. I can plug it back into that, and then I get n class sine 90 minus phi equal to NA sine alpha. Now you're almost done. Okay. This is just the way that I just revised what the Snell's law is about. Okay, that's what we have. Now, here comes the real question of this one. They said they want the ray to totally reflect it at the face AC. What does this condition is telling you? You want the beam to actually not coming out. You want the beam to reflect back into the glass at point P. Does that make sense? So the way that you can start having that condition is you have to hit the critical angle, or in terms of the whole rays tracing and everything, it's just you saying that the outgoing ray is supposed to make a 90-degree angle. That's when you start to get a reflection back. Does that make sense? Okay. So that means the way that you can calculate this one is going to be simple. Okay, let me erase this one. For this particular problem, what they really need, they need the outgoing ray to be, I mean, the way that you want to set up this problem is, the way it's set up here. You want the outgoing ray to be exactly at 90 degrees. You extend this one out to make the alpha to be at 90 degrees. That's when you start to get total internal reflection. Cool. So you just use this as like a boundary, we call it boundary condition. Don't use that one. You're gonna, mix up with the boundary condition in calculus. But that is the condition that you're gonna cross over from having the reflection or not having the reflection. Cool. All right, guys. So what we have to do over here is just set this alpha to be 90 degrees. And that will lead you back to calculate the phi. And at that value of phi, you will have the starting point where you're going to start to get the reflection there. Cool. Already. So now you use the trigonometric identity a little bit. Sine 90 minus phi is just cosine phi. That one is easy. Okay, so that's good. So what you have over here is you plug in the n class 1.5, you plug in the NA1, sine 90 is also 1, and that's it, guys. Cosine phi is just 1 over 1.5. I mean, you can write 1.5 as 3/2, so it's 2/3, and that is it. You get the phi. Okay. All right, that's easy enough. All right, and part B, no difference. The only thing that is going to be different in part B is just think again, Majan. You immerse this prism in water. So the only thing that is going to change is just the, oh, it's supposed to be blue. Oh, I wanted big. Here we go. So what we have here is now you fill, right, the surrounding of this prism by water. So the only thing that's going to get changed for this particular problem is just instead of having air on the second medium, you change the N air into N of water. So that means the equation will look almost the same. So part B, at the same point at P, you have N class, psi exactly the same, psi theta, equal to, now you turn it into N water. Let me put the W subscript in there. And then you take a sine of alpha, which you're going to take this to be at 90 degrees, exactly the same, no change. Cool. So that's it. So you turn this once again into sine of, I mean, everything will look exactly the same, no change. Geometry is exactly the same. The only thing that you just want to change is just to substitute NW for NA, and then you're done. So what you have here is the cosine of phi in this second case is going to be NW, which is the water, divided by N glass. And the water, you look it up in the table, it's about 1.33 approximately, and in glass is 1.5. And then you can figure out the theta in this particular case. You're done. It's kind of quiet here without sound effects. All right, but anyway, see? All right, so I hope by showing you this problem is it's sort of confirmed that application of Snell's law is simple, and then you can extend the Snell's law to take into account the total internal reflection problems as well, by set up the refracted ray to be at 90 degrees. That's all. Any questions so far? All right, so if this is kind of good, and then I think you can see that you use the critical conditions to figure out the I tend to use the word boundary, but that's give you the condition that you're going to cross over from get the reflection or not by setting up the refracted rate to be at 90 degrees. That's how it's done. All right, just to confirm that you know how it's done for sure, try the next one. This is the level of the exam question. So I think it used to be the old exam before, actually. All right, it just maybe changed the configuration a little bit. So you guys try this. Go ahead. All right. Let me answer. All right. So you guys give it a shot and see how it goes. All right. Let me turn off the sound first. Okay. All right, guys. Get the feeling of what the question is about. All right. This is, I would say, exactly as the question that I'm going to show up in the exam because I don't have anything else to ask you. But it just maybe come out as like a different, I don't know, orientation, or maybe I send in the light in a different ways. But the idea is this. The way that just want to make things more complicated is just to look at multiple surfaces and then you just play around with the geometry. That's all. All right. But anyway, the concepts stay the same. Just taking the bam, Snell's law. Try it. In the figure, the light ray enters a glass slab at point A, so it comes from the top. All right. With the incident angle theta 1 given to be 45 degrees, and it undergoes total internal reflection at B. So even though the figure over here gives you the reflection, but in reality, I mean, it's not reality. This is reality. The reality is, in general, you cannot hit the light at exactly critical angle. I don't think that's wow. Yeah, you can get close and you can get some sort of like phenomena at the surface. It can do funny business and other stuff, but in general, for the regular experiments or whatever, you just either get refraction or you get total internal reflection, right? So that means for the purpose of calculation, all you have to do, you can just replace that with this 90 degree. There you go. That is the case that divide between you're going to get reflection or not. Cool. All right. So, I mean, don't worry about the figure over there because you want to figure out what is going on when it starts to undergo total internal reflection. All right. So over here, what we can do is we can start analyzing point A first. All right. So what they want to do is they just want to use this information to find the minimum value of the index of refraction. The reason it's going to be minimum value because, I mean, you start by taking the outgoing ray to be at 90 degrees. That will give you the lowest possible value of n of the glass. All right. And if the n of the glass is higher, it's guaranteed that you're going to get total internal reflection for sure. You guys with me with that? Cool. All right. So let's give it a shot. So at A, okay, you start from the top. You say, okay, NA, because that's out here, that's A. Sine theta 1, that's at the incoming, equal to, now you get into the glass. So let me put subscript G for that. So it's going to be N glass. This is the one that you want to figure out. Times D. Okay, now let me call this alpha again. So you can take the sine alpha. It's the angle with respect to normal line. Cool. Anything else? Well, then that is done. All right, but we have two unknowns at this point. We don't know N of glass, and we don't know alpha. So we need another equation. So let's take this as equation number 1. All right, move on to point B. So let me put a spot right there. So at B, okay, now let's start from the glass out into the air. So glass is Ng. Now you're doing here, let me call this beta, right? We always take the angle with respect to normal line. So sine beta, that's the incident angle at point B, equal to, now you get out into the air once again, but then now you would like to take the condition that you start to get the total internal reflection. So you take sine of 90 degrees. Cool. Suppose you have like a big clap right here. All right, over here. And then you say this is the equation number 2. Almost done, almost done. All right. So what do you need? You want the N glass. That's what you want. So that means you probably want to eliminate the unknown alpha, stuff like that. So how can you do that? There are, I mean, it's only 2 unknowns right now. When I say 2 unknowns, because of this. If you look carefully here, the alpha and the beta, see, they are actually inside the internal angles of a triangle. All right, so that means you know the condition of the alpha plus the beta must be equal to 90 degrees. Cool. All right, so that means your second equation can be written like this. All right, so let me write N glass. That's what you want to know. Now you can turn beta into 90 minus alpha. So you say sine 90 minus alpha equal to N air. You can set 1 to it. Sine 90 is 1. So let me call this equation number 3. And I can write number 3 one more time because you say sine 90 minus alpha is just cosine. So that means it's an N glass cosine alpha equal to 1. I can call this equation number 4. Well, I should have just called this number 3, I think. All right. So, all right, don't call this equation number 3 just yet. All right. Yeah, let me call this number 3. This is more useful there. Okay. All right, so what can you do? Okay, equation number 1, actually, you can write it like 1 sine alpha, sine theta 1, which is sine 45. Okay, I can substitute there. Equal to N glass, that's what you want, and sine alpha. So let me pull this one down here. So from that equation, let me write it in the same order here. It's N glass sine alpha equal to sine 45 is √2/2. Let me call this equation number 4. Too many equations. All right, but I think you see where it goes now. You can solve for, I mean, it's 2 unknowns. It's N glass and alpha. Okay, so if you want to use calculators, now things are going to be easy now because you can do, well, you can take 4 divided by 3. You eliminate N glass. You get 10 of alpha equal to √2/2. So that means from here, you know the value of that angle alpha. And once you know this, you want to figure out the N glass, you just plug into one of these 2, and then you can solve for N glass, and you are done. Right there. Cool. Easy enough, I think. Yeah, not bad, not bad. All right, so this is it, guys. So this is, I would say, well, I wouldn't call this the hardest problems, but as you can probably expect, the difficulty of this kind of problems, I think it's comes from the complexity of geometry, right? Because you only use one relationship right here, which is Snell's law. That's it. Okay, so it just depends on how tricky the question that wants to ask you. Thanks. Cool. All right, guys. Great. Any questions so far? All right. So if not, I think this is it. That is 2 properties that we would like to understand. Reflection, easiest one. Incident angle equal to reflected angle. The second one, refraction, based on Snell's law when you want to do the analysis. Now, what can this thing take you to? Okay, so now it will take you to another application that is going to be very, very close to your everyday lives and everything, which is the formation of images. You use this all the time because you use like camera, right? The way that the camera can capture everything around you is, that means there must be a way that you can pretty much put all the information around you and put it on the CCD, on the CMOS or whatever, and then you capture all the colors and all the stuff. So that's when you want to form your image on the image sensor in your phone or in your camera. All right, so that means there must be a way that you can manipulate incoming information in terms of the light from the object and then try to focus. Now we have the word focus. So you want to focus all those information onto a device that can record all those informations. Yeah. And that is called image formation. Okay. So how to do that? Now you have to, I don't know, have you done this before? But for those of you that still remember, these topics actually popped up since like middle school, because I think this is like a fundamental topics that people would love to cover in science, right? It doesn't have to be physics, but it's just general science. But I'm not sure how deep you get into calculated that until you hit the high school physics. I think you do it one more time. All right, but maybe some of you still haven't tried this before. So let's go through this one slowly, shall we? All right, just want to make sure that you understand the mechanism behind this whole thing. First, look at this. This is how image is supposed to be formed. All right, so now first thing first, you have to imagine that there is an object. You want to capture the image of these objects. What actually happens? First thing first, there must be a light coming out of the object. And of course, the object probably cannot illuminate itself, or there's no self-illumination or anything. So that means in general, you have to flood the light onto the object. So you must have some environmental or ambient light. That's why you need a flash if it's in the dark, or you have to look at it in the daylight or whatever. All right. But anyway, let's say you have a light shining on it, and then that object reflects out the light. So that means now we can skip that process. And let's say there is a light coming out from the object. Sounds cool? And to do the analysis, you have to look at one spot at a time. And if you can make things work at one spot, it will work at all the spots. And that means you can reconstruct the actual image on whatever the sensor, the paper, the screen, or whatever. All right. So that's why the way that you can the way that you analyze this one is just to pick a spot on an object and do the whole analysis with that point. And that's it. All right. And then we can assume that everything else work exactly the same. So you pick a point on the object and see how things go. And the way that you do that is just you draw like a rays of light. That's it. All right. And because you put a point into that, you put a point onto that spot, you can assume that it's a light source that is in a point source configuration. So it means you have a source that looks like a spot. And we learn a little bit from sound that if you have a point source, then the sound will be generated in all directions. Same thing over here. So if you say that, hey, the light coming out from that spot on the object, you assume that the light will coming out, sort of like diverge out from that spot in all directions. Cool? All right, so that's what you do. You just draw, pretty much like draw. It's the light will go everywhere, actually. It will go every direction. But because we want to know where it goes through our devices, for example, we will learn more about this one very soon. If you have a device called lens, okay, if you have a lens, and then what you want to know is, hey, what happened when the light go through lenses? So you just pick those rays and then you just do the analysis, or maybe you look at that. I want to see this one, or there's a huge one. Sorry, maybe too big. Sorry about that. All right, so you might just say, hey, I want to see what is going on with this ray. It's going to hit the lens. And because lens is made out of transparent medium, maybe glass, maybe plastic, polymer, or whatever, so you start to have the refraction on the surface. So it will reflect. Here, let me zoom in here. So it will reflect on the first surface and hit another surface. It refract again out. And then you just stretch the ray outward right there. Cool. So you see that the overall effect of having the lens in between is you bend the light. And now you pick another ray. Let's say, let's look at the bottom one. Okay, this one hit the lens. It go refraction on the left surface and then refraction one more on the right. And eventually it refracted out in this direction. And here we go. This is the key. If you have this type of the ray that start from a point and you can end up at a point, that's how you think of it. Like you transfer the information of that point on the object into another point which look exactly the same on the right side. And we're going to call this, that is the image of that object. I don't know, I'm going too long or not with this, but I hope just to take care of some of you that might have not done this kind of analysis before. So that's why every time that you can pinpoint a position where the rays are crossing each other on the right-hand side, that regenerates the point that come from the object on the left. That's when you say you form an image. Okay, cool. All right, all right. And of course, by this whole thing that you're doing over here, you can analyze other ray. It doesn't have to stop at just those two rays. All those rays supposed to do, and then it eventually, if you're going to have the image reconstructed at a perfect image, all the rays that you pick supposed to cross at exact same spots. That's why we call this spot image is in focus. Does that make sense? Because if you slide this, this could be a screen or whatever, if you move that screen a little bit forward like this, see, the spot on this screen are not exactly at the intersection. So you are going to get a blurred image. Does that make sense? Or if you move that paper a little bit backward over here, then those spots will not be exactly on top of each other. You can have another blurred image. So you just have to move your screen around until you exactly here where all the rays are crossing at one particular point. And that's when you have image in focus. All right, that's it. That's what I want to say. That's what it means by image formation. You are looking for a position where the rays are crossing or intersecting each other. Okay, we call that, like, you can think of it like that is a point where you reconstruct image perfectly, 100% clear image. All right, but anyway, there is another possibility here. Look at this case. All right, this is a very common case here. You have a point source. Now you okay, well done, that's good. And the ray is supposed to go out in all directions. There, crazy here, there, all over the place, right? But then let's say you hit another type of device. It's called mirror. The mirror reflects light according to law of reflection. The incident angle equal to reflected angle. But then you look at it, well, I can trace that. If you look the one in the bottom, it will reflect down here. If you look in the up top here, it will reflect here. It will reflect here, on and on. This reflect back on itself. This go up. Do you see that the reflected ray is diverging? You see that? Okay, let me highlight that. Look at that. It's diverging. It's not converging into a point. It's diverged out, 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 out. So that means in this case, you will never get the rays to intersect each other ever. No way. Okay, no, because they are diverging at this point, all those rays. So the question is, what happened to this? That means, are you not going to get any images or anything? But no, the answer is you will not get a real image. A real image. This is real because it came from the actual intersections of the rays. But in the bottom here, no, you won't get something real. But the question is, what is happening? If you place your eyes here, your eyes intercepting those diverging rays, it turns out your brain will interpret that ray of light in the sense that it will interpret that the source of the image come from, you have to extend those rays. You can call it like extrapolate. You can extrapolate those rays until you find a point that is virtually virtual. It's like a virtual positions. It's like, yeah, your brain will think that the light coming out from this point source right here. And because that intersections came from your own extrapolation, is not a real crossing of those rays. You are looking at a virtual image. Cool. So I hope by sort of I might spend too much time on this slide, but I think I just want to make sure that you guys understand the difference between what is real image and what is virtual image. Okay, so conclusion is this: the real image must come from the actual intersections of the actual rays. That has to be. It's real. So when it's real, it means you can place your hands there. You can put the screen here. That means whatever the image that you can see from the screen in front of your classroom, like you do a projector and the projector just projects the PowerPoint or whatever the figure onto a screen, you can place your hands there, all right? And then you can put whatever the image on your hand because it's real. You can put the real stuff on the real stuff. But on the other hand, if you are looking at this, the diverging ray, those rays will never cross each other. So that means the intersection that you are getting is just by your own extrapolation. It's not real. So you cannot touch it. And this is exactly what you see yourself in a mirror. You can see yourself in a mirror, but you cannot touch it. You cannot do anything with it, but you can just observe your reflection from the mirror by eyes. That's it. All right. So that means your image through the mirror is a virtual image and it's not real because light gets reflected to the front side of the mirror. You're never going to get a real actual intersections of the rays. Whew, got it. All right. So I want to take this thing slowly because I just want to make sure that you understand the difference between these two. All right. But I hope this is it. It's clear. All right. For real image, you need a real intersection. For virtual image, you have to extrapolate the rays yourself. All right. Now, with that allow us to now start talking about, there will be two main stuff that we are going to discuss. It's either the mirrors that do the reflection or lenses that do the refraction. You see the difference between the two? Okay, mirror reflects light. Lenses refract light because lenses are made of transparent material. That's it. So that's why we had to start talking about the law of reflection and refraction so we can describe what is going on with the mirrors and lenses in the image formation. All right. The first kind of image that you're going to, sort of like be able to answer right away is it's the plane mirror. The one that you look yourself in the mirror, just a regular mirror right there. So with that, it's super simple in the sense that because the mirror is flat. So when it's flat, the law of reflection just starts happening exactly the same at all points. So that's why we call the mirror reflection or the mirror image of each other. So you can imagine that if you take the mirror to be the boundary between left and right, it will look exactly the same because we call this a mirror image. So with that, it means if you place an object at a distance P away from the mirror, of course, you can expect that you're going to get an image of that object at the distance exactly the same as the distance that the object is being placed in the front. Okay, so we're just going to have here P over here, that is the object distance. And I over here, you can call it the image distance. Cool. All right, so for plane mirror, there's not much to it. All right, and we already knew that the image that you are looking at is a virtual image because the reflection gives you the diverging of light. Light never converge after reflection. All right, and in other textbook, they might not use P and I, and then I think these are being used interchangeably. Sometimes they use S and S prime. Some book use U and V. Some book use O and I, it doesn't matter. All right. So anyway, one is going to be object distance. The other one is going to be image distance. All right. And in this slide, we just sort of like use them interchangeably, or it depends on some of you have already used, some notifications or some symbol differently back in the high school physics day. So use whatever you feel comfortable. Okay. All right. So with this, plane mirror is kind of like boring because Adan, this is fine. object distance equal to image distance. Image is definitely virtual because of the reflection of the mirror. Now, things start to get more interesting when the mirror is curved. Here we go. All right, and that is kind of cool because when it's curved, now you bend the light to guarantee that you somehow, you hope, you're going to get some intersection of those rays, either real or virtual somehow, but it's gonna do something. All right, funny business start to happen. So we all look at the spherical mirrors. All right, at first we're gonna take spherical because, all right, we'll do some comments on what is going on with this later on, because a sphere is not perfect one that give you a perfect spot of the focal point, but that's all right, that's later, right? To the first approximation, spherical mirror can behave like this. It's curved. So if you send in the light in the horizontal direction, okay, it's going to reflect downward, no problem. If you do drawing another ray, hit the mirror, it's going to do the reflection, no problem. Okay, so if you have a horizontal ray that goes in, and then this horizontal line, you can call it, this is like a central axis. It's like you cut your mirror in half horizontally. Okay, and then when the light just come in like a parallel beam, parallel to the central axis, then the ray will reflect it and intersect at a single point. Here, point F that's showing right here. And that single point right there, we call it a focal point. Cool. Now that is a focal point. And the distance from that point F, the focal point, to the center of the mirror, we call it focal length. All right, so it's like a distance from the center of the mirror to the focal point. We call it a focal length. All right, now by the law of the reflection, guys, don't forget we have to draw the normal line, right? And the incident ray equal to the reflected ray. Everyone cool with this? Okay. Now you think about it, Bajan. You draw a normal line to a sphere or a circle. Where does this normal line go? If you extend this one out, and if you do the same thing underneath here, you draw a normal line. Okay. And now, if I want to do it properly to make it a little bit nicer, that normal line here, that normal line there, by the property of a circle or a sphere, it will go through the center of the sphere. Cool. So that's why we can call the C point over here to be the center of curvature of the mirror. All right. And that distance from point C to the center of the mirror, we can call it the R, which is the radius of curvature. Cool. And by the law of reflection, because if this is theta, this must be theta, it's half. So that means you know right away the focal length supposed to be half the radius by the law of reflection, right? It's just cut the angle in half, so it's going to cut the distance in half as well. So you get the first relationship right here, right now. That the focal length is just half the radius of curvature of that sphere. Cool. All right, but then you still have a variation here. You have two choices that you can make. Majan, the curvature that you pick over here make the light reflected ends cross in the front of the mirror, right? So we call this a concave mirror, or it's easier, is converging, because if you send in a parallel beam, it will converge into a point at the focal point. So that's good. But then you can pick, I can do the opposite curvature. I can do the curving like this. So with that, if you send in a ray, let's send it in. All right, the upper one parallel to the central axis is going to bounce off, right? Law of reflection. Okay, same thing with the second one here. You send in the second one here, it's going to bounce off like this. And we already knew by picking this kind of curvature, the ray that coming out of the reflection is going to diverge. So what do? You have to extrapolate those rays yourself. See? So now you start to see that there is point F. which you can call it a focal point as well. But this focal point is not real, right? Because it came from the extension of your rays. It's not real because light never gets toward the back side of the mirror ever. Everything gets reflected to the front. So if something is about to happen behind the lens, that's not real. No way it's going to be real. So that is why we're going to call this I mean, you don't have to call it a virtual focus, but you can call this is a focal point. But the focal point having the focal length extend behind the mirror. Cool. And same thing, if you go twice as big, you're going to go to the center of curvature. No big deal, because twice the focal length give you the radius of curvature. So now you already see two types of mirror. The right side over here, we call it a convex mirror. And if you somehow confuse like which one you're going to call concave or convex, just call it diverging lens. I mean, diverging mirror, because it's diverged out the rays of light. Cool. All right, so these conclude two types of mirror and the behavior of the mirror that it has an effect on the parallel beams of light hitting it. Once again, just to conclude before the break here, the concave mirror, the converging mirror is convert that parallel beam into a spot at the focal point. For the diverging mirror, it's diverged out the ray, okay, but it has a focal point behind the mirror. All right, but this one is like easier done. You send in just like a parallel beam of light, so this one is fine. So what's more interesting is if you have an object instead. So when you have an object in front of the mirror, now you are no more sending in a parallel beam of light. You guys with me here? Because look at this one. We're going to start to do the analysis, right, after the break. When you look at this one, you have an object, as I already said. You only pick a point from the objects to do the analysis, and everything will follow. So the way that we do it is we're just going to pick the tip of this. Let's like, Ajahn, let's pick that tip up here. And let's trace the rays that are coming out from that tip of this object and see where it goes. First thing first, all right, you can draw one ray that coming out straight. This one, you know, the behavior of this one is it's going to bounce off and cross the focal point. So you can call this like a ray number one. And then you say, well, again, I just need one more because we just want to know where are they going to intersect. So the only way that I can do is just like, you have to pick one more line. So I can pick this one. The ray that actually going through the focal point first and hit the mirror. Can you guess what happened here? Of course, Ajahn, you hit the focal point first and hit the mirror, it's going to get the reflection out parallel. So you start seeing this, see? The ray that coming out from the tip of the object is no more parallel beam. It's the diverging beam. So that's why you're going to hit a different point of intersection here. Okay, let me highlight that one. Here. That's where the ray number one and ray number two are crossing. And that's how you pinpoint the image location. All right, so I'm just going to stop right here. But I think you guys start to see where we are about to go here. See, you place an object at the distance P away from the mirror. You call this object distance. And you just somehow try to find where the lights coming out from this object are going to intersect. If you can figure that out and it's positioned right here, you make a measurement from that to the center of the lens, you get the image distance I. And that will be a relationship between the P and the I. And once you know this relationship, your life is good. We're done. All right, so I will reveal what kind of relationship between P and I is supposed to happen right after the break. Sounds cool? All right, guys, take 15. All right, a lot of talking today. All right, so by these techniques, all right, just doing the ray tracing, you just sort of like draw the rays and see what happened when it hits the mirror, get reflection, and then you find the intersections between any two rays. You just pick two. You don't have to do more than two, actually. For example, in reality, okay, some of you might just sort of like wondering, if I draw other lines, okay, with the law of reflection, it will just come back to this. If you draw another one, it will just go here. You see what I'm saying here? So you can draw the rays as many as you like, but they're all going to intersect at a single point. And that point, my bad, sorry, right? Wrong one, sorry. It's supposed to intersect at the image location. My bad, sorry, here, okay, right there. It's supposed to be at the tip of the image there. That make more sense. All right, there you go, something like that. Here we go, and it's just gonna cross at the tip there. All right, so this better. So no matter which rays you try to draw with the law of reflection, they are going to meet at a single point, and that point is the point of the image. All right, cool. So that's what we sort of like get an idea from. And then you just keep doing this for no matter it's a concave or convex mirror, same thing. But what you can notice over here is because this one is coming from the actual intersections of the real rays. So you can call this a real image. Now I hope you see it. All right. Okay. And down here, if you do pretty much the same thing with the diverging mirror, the convex mirror, so you can draw as many rays as you like. You can do this. Okay. And the ray is going to extend out like that. You can do here. It's going to extend out like this. As you can see, the reflections from this diverging mirror is going to be a diverging ray, but you have to extrapolate yourself. So I'll do this, a faint line here. If I extrapolate there, extrapolate here, extrapolate the line here, extrapolate the line here. There you go. All right, so that will be the image location. However, because of that extrapolation stuff that you do, so what you're getting over here, this is a virtual image. And now, if you measure the distance from the object to the center of the mirror, you call this the image distance, right? And if you measure the distance of the image to the location, to the center of the mirror, that is your image distance. I think personally, I actually prefer P and Q. I think, not P and I. I don't know why P and I don't know. It depends. You can use whatever you like. But I think I kind of familiar with the P and Q, or at least S and S prime. I think maybe that's the combination that I use the most. All right, but anyway, you know, one has to be for the object, the other distance is for the image. All right, and the figure on the right just showcasing that you can pick any two rays to determine where the location of the image is. Now, what else that you can talk about the image? If you look in the upper case, you see, okay, Ajahn, is real image and all this stuff. However, you can see that the size, look at the size. Whoa, the object is tall. The image is kind of like, no, it's not that tall. So you have the reduction in size. So that means the image that you see is going to reduce in size. So you have a reduction over here. Same thing down here. You look at the object is kind of tall, but the image is not as tall. So you have, once again, the reduction in size. So that means it depends on the location of the object. It will have an effect on the final image. It's either real or virtual, plus you might get some magnification or reduction of the image. Sounds cool? All right, so I think the uppercase, the one with the converging lens, I think the scenario that you probably have seen before was the one that you use like a cosmetic mirror, that it's curved a little bit, and when you put your face in front of this kind of mirror, it will blow up your face hugely, and then you can do the whatever, the makeup, or you know, do that something there. All right, or the one with the diverging lens, I'm sorry, diverging mirror was the one that you see at the corner of the street that allow you to see the other side of the road and stuff, like is there any incoming cars or not. And as you can notice that the image in that mirror is smaller, okay? So you might be wondering, well, Ajahn, this case is not exactly the one that you see over here, because you see that this image that you see from the mirror is magnified. But the thing is, this scenario is actually the backward scenario of what you just did over here. So what you see over here is like you have an object here and you have an image here. Does that make sense to you? Because light travel in a straight line. So that means if you place an image at one point, I mean, if you place an object at one point, you generate an image. You can switch these two places. It will be exactly the same as like tracing the ray backward. Is that cool? All right, light from the law of reflection. You go out, you go in, go out in the same direction. You can reverse the whole directions of light, and you get exact same location of the intersection. All right, so for this particular case, it's more like you put your face so close to the mirror, so that's why you can see the image. Well, it's not exactly this one, right? I don't want to see that one, but all right. I mean, this is my bad. I know this is not good. All right. I actually I spotted this one since last trimester that I shouldn't put the scenario of that cosmetic mirror and those stuff for this particular diagram here, because this diagram give you the real image, but the image that you see from the mirror is still virtual image. So this is not good. These are not related. These two are not the same cases. All right, so my bad. This is my bad. Sorry about this. But anyway, we'll have the full analysis of what is going on. All right, but at least the point of this cosmetic mirror over here, just want to know that's where you can find out the concave mirror. That's where you can find it somewhere nearby. Okay. All right. So how are we going to do that? We're not going to keep drawing this rays because it's kind of like that is it's a job for computer, or I mean, you use software to trace all those rays. You're not going to be able to do it by hand. All right. So the way that we can do, we want to do it in an analytical way. So we want to do the analysis using some equations, not by drawing rays and all this stuff. So what we are trying to do is we want to know the relationship between the image distance. Okay, sorry, I say something and draws one other thing. The object distance and the image distance and the focal length. Here we go. These are the three stuff that are related and allow you to figure out the location of the image. It's right here, guys. The equation is simple. Okay, let me fast forward first. I'll go back to magnification here. This is it. It's simple as this. All right. It turns out the inverse sum of this is image, object location. So this is an object distance. This is the image distance. And this focal length. That's it, guys. It's that simple. 1 over P plus 1 over Q equal to 1 over focal length. Done. Let me call this equation number 1. We're supposed to have a clap. Okay. All right. So this allows you to get the relationship between the P and the Q and the F. All right. And you only need one more equation, guys. That's all you need. Here, we already said about the magnification, right? So if we want to take care of the magnification, it turns out the image size over the object size will give you the magnification for sure, right? Because I mean, of course, if you can take this ratio, you know what kind of sizing you're gonna get. And that is just gonna be the image height divided by the object height. Okay, so right here, this is the image height. This is an object's height. Okay. However, the good thing about this one is due to a simple law of the reflection and everything. So it turns out this ratio will be exactly the ratio of the image and object distance. How easy is that? All right. However, I just want to make this equation a very, very, I mean, it gives some utility to this equation as well. Not only just you can calculate the magnification. If you lift that absolute sign out, and I just want to calculate pure value of M with the sign attached, the equation will look like this one that I'm going to call it is equation number 2. This is the magnification equation. It turns out you just attach the negative sign in the front and you take the ratio of the image distance divided by the object distance. You will get the M in magnitude and sign. And the sign will help you determine, is it going to be the upright or inverted image? See this? the image that you see over here, not only it's smaller in size, but it's inverted, it's upside down. So that means with the M equation, along with the sign, you will be able to tell at the end, is the final image, is the upright or inverted. This one is upright. The first one is inverted. So the sign will tell you. That's all I'm asking from you guys. I only ask you 2 equations. You can solve, I wouldn't say every question in the universe, but I mean, that's, you should be able to do the exam, let's say. All right, so first equation, we call this the mirror equation. Very simple to use, 1 over P plus 1 over Q equal to 1 over F. And the second equation is the magnification equation that come with the sign in the front, allow you to get the final answer. Now, the most difficult thing of this one is what? To use this equation, right? Either one of these equations, the P and the Q has to have sign. The complication is just at this point. So this table right here give you the conclusion about the sign. When I say what about the sign, what the sign? What is the sign? The sign is this. And I will show you with the example. I think that's the easier way of showing you how to use this equation. But the point is this. I will give you a rough concept of what is this equation is about in terms of the sign. Think about it, guys. When you have light coming from the left, hit a mirror, whatever happens after the reflection, light's supposed to stay in front of the mirror. You guys with me? Right? Because of the reflection from the mirror. Light has to stay on the left side of the mirror if the light coming from the left. So that means if you are going to get a real image, it has to show up in front of the mirror. You guys with me with this? You will never be able to get real image behind the mirror. It's impossible because there's no light behind the mirror, guys. I think the logic is kind of like straightforward. You're never gonna get light behind the mirror because everything gets reflected out in the front. So that means if you were to get a real image, that real image is supposed to show up in front of the mirror. All right, and that's why we are going to call this location the location where light is actually there, to be positive side of things. Okay, stick with me here. All right, I don't know, is this a right way of well, it's the right way, of course, but I don't know if this is a good way of showing you how to use this one, but it seems to work really well with me for many years, for my whole life actually. And the position or the side of the mirror where the light shouldn't be there, that is going to be negative side. It's unreal. It's not real. So what I can say is like positive is real and negative is not real. That's what I'm saying. All right. So that's why for the image, so I have to emphasize talking about the image. The positive side for the image is the front side of the mirror, and the negative side of the mirror of the image is the behind the mirror. And with that agreement, you can call it, if things were to be real, it's supposed to show up on the left or in the front. And whatever shows up behind the lens, that is going to be virtual. For sure, it's guaranteed. All right, guys, just to test this agreement here, go back to our diagram here. Can you see this? See, over here, the image show up in the front of the mirror and it's real. It can be real. It's real. Right? And if somehow you have an image show up in behind the mirror, it's guaranteed to be virtual. Nothing else you can do. That's the way it goes. Cool. All right, guys. That's what I would like to conclude over here, and I'll show you how to utilize this, how to interpret this, and what this equation will give you. Good things is like this is like buy one get one free, guys. If you understand how to work with the mirror equation, you will understand how to work with the lens equation right away. Yeah, there's 2 in the price of 1. Seriously. All right, I'll show you how it's done. All right, give you this. Almost done, guys. Stick with me. All right. So If you understand this problem, I can transfer everything toward the lenses using the same logic. Bam, let you guys go. All right, you have a concave spherical mirror. All right, and let's see if my logic works. All right, I try to introduce this topic in a natural way so you don't have to memorize stuff. Okay, you have a concave spherical mirror. So I draw this figure over here. With the radius of curvature, R is 20 centimeter. So that means you know the focal length to be exactly 10 centimeter, right? Half the radius. Find the location of the image of the object when the distance of the object is at, let's start from part A, 40 centimeter. Guys, give it a shot. So that means P is positive 40. Why is positive, Ajahn? Of course, is an object distance. And when the object is a single object, is in the front of the mirror, why would you put negative sign to it? It's a real object anyway. Okay, we'll discuss about virtual objects later. That's after, right? After we're done with everything. But just a single object in front of the mirror, the object distance is supposed to be a real object distance. Okay, so what you want to figure out is the Q, the image location. Yes, that's what you want to figure out. Now, what you want to know is, hey, Ajahn, what is the focal length? Now, here, start with me. You put an object right here. The focal length, let me put it here. This is 10 centimeter. Let me call that F focal point. Twice of that, that is center of curvature at 20. But now you place your object 40. So your object is right here, 40 centimeter, far away a little bit. Cool. So what's missing over here is, Ajahn, do I have to do anything with the focal length F over here? The answer is yeah, because you have two types of mirror, right? The concave and convex, right? The converging and the diverging. Can you guess if the focal length of this concave mirror show up in the front, or that means the focal point is in the front of the mirror? Should you call this a positive focal length or negative? Can you guess? Yeah, it's supposed to be positive. Why? Because we already learned about if you send in the light, it's supposed to cross here. Sending the light is supposed to cross there. Is a real focal point. That was the reason why we call it a real focal point. That is because it's the place where the light is supposed to cross each other for real. So that's why we are going to use this to be positive 10. You can mark 10 to be positive 10 focal length right there. Cool. That's how it's being used, guys. So if you look back in this table, see, focal length, it's positive when the mirror is concave. But instead of memorizing this table, I'll just use a simple logic. The focal point is in the front of the mirror. The front of the concave mirror, it's the front of the mirror. It's a positive size of thing in the image formation. So that's good. I'll take positive. So that's it, guys. Apply mirror equation, 1 over P plus 1 over Q equal to 1 over F. So from here, 1 over Q is just 1 over F minus 1 over P. And what you're getting over here is 3 over 40. It's still positive, guys. Sign is important here. Okay, so over here now you get 3 over 40. Don't forget to flip it over. So your Q is positive 40 over 3. So it's about 13.3 centimeter, let's say. So what does a positive sign mean? It means it's in the positive side of the image, and we already agreed. When the positive, when you have talk about mirror and it's positive, positive means it's in the front. So I can pinpoint right away. The image supposed to be around here, guys, 13.3. See, it's in the front, positive. Now, part B, not part A. What about the size, right? Because they want to know, is it real? Is it virtual? Can you tell, is it real or virtual now? But then it's positive, so it's supposed to be real. Image is real. It's positive, it's real. It shows up in front of the mirror, right? And it's upright or inverted. Here, let me give you this. I can continue on with the M equation, the second equation, negative Q over P. Plug in with the sign. Negative positive 13.3 divided by P, the distance of the object 40, right there. Okay, so what you get at the end is negative 1/3. So what does it mean? It means the magnification is 1/3. So that means the size of the image is 1/3 of the size of the object. So that means if the object is this tall right here, this tall, the image will be 1/3 of that size. But then you have a negative sign here. It means it's inverted. So that's it. I can draw right away. The image is down here. Mini one here. It's, I don't know, can you see it? It's 1/3 of the height and it's inverted. That's it. You're done. Got that one? This is how it's being used over here. Okay, try again. Part B, All right, follow me here. So let's do part B. All right, I think you start to see how it goes now. P is definitely still positive all the time. Q, this is what you want to figure out. F is positive 10 centimeter. Yeah, cool. So you do the same equation thing. So 1 over Q equal to 1 over F minus 1 over P. All right. Oops, sorry. P is now 20, guys. Sorry, my bad. It's 20 now. Part B, there, 20 centimeters. So now you place your objects at 20 degrees, 20 centimeter. All right. Plug it in. 1 over F to be positive 10 minus 1 over P, which is positive 20. What you get over here is 1 over 20. It's still positive. So what you get at the end is Q is positive 20 centimeter. Real or virtual, guys? Real or virtual? But then, yeah, positive. So it's real. I think I have to do better with the color coding here. I try to improve this one, but it's just all over the place. All right, but anyway, the positive sign for the image means the image is real. So it means it's going to show up in front. Where? 20 centimeter. So now I know the image will be at 20 centimeter in front of the mirror. Upright or inverted, keep going, guys. M is negative Q over P. Negative Q is positive 20. Let me omit the unit here. Over 20. Positive, that's for P. And that's negative 1. Whoa, what does it mean? The negative, oh, I think, is that screen frozen here? Uh-oh. All right, but anyway, negative 1 right there means, first things first, negative mean is inverted. So let me point here, inverted. But the magnitude is 1, so it means there's no magnification or the reduction. The size of the image is exactly the same as the object. So do you can guess what is going on in this case here? You place your object right at the center of curvature. From the law of reflection, you are right at the center of a sphere. So the light will reflect the sphere and hit back to yourself. Back to yourself, it just flip over. So that's why your final image is just upside down. But no magnification or reduction or anything. It's the same size. You just flip it over because you go through reflection from the mirror. So the image location is right on the center of curvature. That's all. I mean, you guys follow, right? All right. And now part C. I think part C is going to be the weirdest because, Bajan, let's place it at the focal point. That's going to be bad because you set your object at the focal point. You guys can guess that the light coming out of it will reflect parallel outward. So you're not going to get anything. So let's show you that is the case. P is now positive 10. Q, you want to know. Focal point is positive 10. And now from the equation, the mirror equation, 1 over Q equal to 1 over F minus 1 over P. See, it's 1 over 10 minus 1 over 10. You get 0. So that means your Q is infinite, which is, all right, we expect that when you place a point object at the focal point, the light that coming out from that focal point will reflect that parallel outward. So you're not going to get image somewhere except so far away. That is indication of It's a parallel beam outward. You're done. So you don't have to talk about the magnification or anything. You're not going to get anything out of it. It's a parallel beam. Make sense? See, it's not that bad if you only apply these two equations with the knowledge of how to stuck in the sign. Just use the correct sign and you're good. You will know exactly what is the end result are supposed to be. All right, and now it's the bonus time. Once you understand how the mirror works, the lens will be automatic. Let me introduce to you right now, and let's see how quick you can understand lens. All right, and for now, I'm just gonna call it thin lens, but I think to sort of like modify or sort of like elaborate on why it has to be thin, it has to be next time. All right, we spend a little bit more time with that in a complicated setting. But for an easy setting, the lens is just a piece of a transparent material that have a curved surface, just like in mirror. All right, but the curve, it's just going to go a little bit backward, because if you have a curve that go in this direction over here, and of course the other side should be curved like this or straight, or doesn't matter, as long as the overall thickness at the center is thicker than the rim, you're going to have something is called converging lens. The reason is because the light that gets into this lens get converged into a point. That's why we call it a converging lens. See? The interpretation of everything, I mean, sort of the terminologies that we used before can be used here. So the distance from the focal point to the lens is the focal length. F, same F, it's the same focal length. All right, so if you pick your lens to curve the other way around, the other side, it could be curved like this or curved whatever, a flat, doesn't matter, as long as the center is thinner than the rim. This lens will perform like a diverging device. So it's going to be a diverging lens in this case. So the light that hits will diverge out. So you do the same trick. What did you do? You extrapolate those rays, extrapolate yourself, extrapolate backward here. Oh, what did I do? What did I do? So, yeah, you extrapolate backward, and they are virtually crossed in the front. So once again, you can name this to be your focal point, F1 over here, and its distance from focal point to the lens, you can call it focal length. So concepts of the focal length is exactly the same. And the concepts of the image is going to be the same. What is this? This is real. So you can expect that the focal length of the converging lens is supposed to be positive. It's real. And the diverging lens, this F is supposed to be negative, because you have to extrapolate. You have to extend your ray by yourself. This is not real. So this is going to be virtual focal point. And you use the same trick, guys. Yeah, last one. Light get through the lens, never get reflected. Light, if it's going to be real, it's going to happen behind the lens. You guys with me here? Because light has to penetrate through the lens. It's a transparent medium. You will never see the light in front of the lens anymore. It's through and through, no coming back. So that means if you were to get a real image, the real image is supposed to show up behind the lens. So the back side of the lens is supposed to be a positive side for the image, which is opposite to this case. That's all. That's all you have to keep in mind. Mirror reflects. So whatever is going to be real is going to show up in the front side of the mirror because of the reflection. But when you do the lens do refraction. Light's supposed to go through. So anything that's supposed to be real, it's going to happen behind the lens. And everything that shows up in front of the lens, that is not going to be real, because light will never be able to come back here anymore. So the image that show up in front of the lens is guaranteed to be virtual. You put a negative sign in there. See? Bonus time. You learn one, you learn two. You know how the mirror works, you will know how things lens work. The only thing that's different is you take the positive side of the image to be behind, not in front anymore, because you get the penetration of those light beams. Cool. And everything else works exactly the same. What does it mean? I mean, you can do the ray tracing if you want, right? You can trace, but everything, instead of reflect, you do refract. So you send light through the other side. And see, you have two equations exactly the same. Not the shape of the equations look exactly the same, except we're going to call this lens equation. That's fine. Use the same. And this one is a magnification equation. This is also fine. Okay, and the agreement of the sign will be exactly the same, except you just have to make sure that you understand that whatever is going to be real is going to be behind the lens. This is real. Whatever for the image that happens in front of the lens, that is going to be virtual. Positive signs on the right, negative signs on the left for the images. Cool. All right, I'll show you how it works, and I think you're going to be happy with this, or maybe I'm happy with this. Guys, last one for the day. All right, and we're gonna show you a more complicated problems and with a discussion of some finer details, just a little bit. But I don't want you to go further than this. I think if you understand how to apply this one, and then next time we just look at a simple combinations of the device, combination of these combination of these lenses or mirrors to generate some instruments or devices, and you understand how this whole thing can be used to analyze the final images. I think that's good enough for me, right? Don't need to go too deep on this. All right, guys, give it a shot and see if this works for lens. An object is located 20 centimeters to the left of diverging lens. All right, so let me draw that for you. You have a diverging lens. It can be any shape, but in general, you just write the center to be thinner than the rim. Now it's a focal length is given to be 32 centimeters, but it's a diverging lens, guys. See, if it's diverging lens, so it means the focal length is going to show up over here. That is your focal point. So that's why don't forget it's going to be negative. Yeah, see, by understand the logic of the sign of the image, you can pretty much assign the correct sign into this parameter right away, right? By understanding that it's a diverging lens. So it means your focal point is in the front. Whatever shows up in the front for the image, that's a negative side of things. So you just put a negative sign into it. So I don't know if this works for you, but if you want to memorize, that is fine too, because in this table, you say focal length is positive for the converging lens, negative for the diverging lens. But for me, I always take into account the proper the proper side of the image. I don't know how to call it. It's like where the light should be, that is where the positive side is gonna follow, something like that. All right, guys. So now we can pinpoint that your focal length for this diverging lens is negative. It's always negative for the diverging lens. Now the object is located at 20 centimeters. So focal distance is 32. So your location of the object is supposed to be, let me write somewhere here. Let's say that's okay. Let me write a little bit taller. Here we go. I put my object right there, 20 centimeters. So it's a little bit closer. It's closer to the lens than the focal point. Focal point is at 32. So this one is at 20. Okay, so this one is 20. Very good. And that one is 32. There. All right, now determine everything. Location and magnification of the image. Go for it, guys. 1 over P plus 1 over Q equal to 1 over F. There's only a single object here. So your P is just positive 20. This object is a real object in front of the lens. Plus 1 over Q, this is what you want to figure out. The focal length is negative 32. And from here, you can figure out the Q by doing some mathematics over here. Okay, if I can do this correctly, I hope. It's negative 52 over 32 times 20. All right, I'll just do some simple math here. All right, and the Q is, don't forget to flip it over one more time. So it's going to be 32 times 20 over 52 with the negative sign. All right, guys. So how much is it? Let's say approximately about 12. Can I say that? Approximately. Yeah, pretty close. It's about 600 something divided by 52. Yeah, that's roughly about 12 centimeters. So that means Q is negative. What does it mean? It means it's gonna be virtual. And what does the negative sign mean for the lens? It means it's, of course, it's virtual. It's gonna show up in the front. So that 12 means the image location will be here. 12. See that? It's in the front. It's virtual image already, for sure. Okay. Now you use the second equation, the magnification equation, negative Q over P. Negative signs there. Q, you just say is a negative 12 over P. Object distance is 20. So what you get at the end is plus 12 over 20. This is approximate, right? Because it's not exactly this. But anyway, you get positive 0.6. Wow. What does it mean by 0.6? It means it's 60% as tall as the object. It's 1/6. I mean, it's 60% tall relative to the height of the object. All right, so it's going to be a little bit shorter. And positive means upright. And that's it, guys. I can draw it right away. Here. Done. Big hand here. Big hand here. Okay. So by applying these two equations, the mirror equations and the magnification equation, you know right away the image at the end is 12 in front because it's a virtual image. 60% height of the object and it's upright. You are done. Woo. All right, guys. And that is it for today. Sounds good? All right, guys. Any questions? I think this is kind of light and breezy. Yeah. Okay, good. So I hope the sound effects, it's kind of like no today. There's no sound effect, but I think the material is still, you learned something today, I hope. All right, guys. So if no further questions, that is it. And I will see you guys, next week, right? On Monday. Okay. And all right, if we don't have any changes or anything, so the second exam will be on 26th. All right. And the score for the first exam should be out, I think, early next week. All right. I'll try to work through the weekend. All right. Okay, guys. Thank you for sticking around. I'll see you guys next week. Bye-bye. Thank you.